What color are sunspots? Can alien civilizations detect the radio waves that we broadcast? How do gravitational assists work? All this and more in this week's question show. It's time for the question show. Your questions, my answers. As always, wherever you are across my channel, if a question pops in your brain, just write it down. I'll gather them up and I will answer them here. Now, just a note, we record this show live every Monday at 5 p.m. Pacific time. So if you want to come, join the live show, ask your questions, see follow-up questions, chat with other people who are watching the show. You can do that here on my YouTube channel, live every 5 p.m. Pacific on Mondays. Now, I say that YouTube will give you a warning when it's about to happen. That is, of course, a terrible lie. YouTube will not do that. They will tell you several weeks after the show happened and it's too late for you to watch it live. So put it in your calendar. We're here every Monday, 5 p.m. and there should be an event on the channel for you to be able to go. All right, let's get into the questions. Our graph. We see lots of pictures of the sun in yellow with black sunspots, even though the sun is really white. So in reality, what color are sunspots? Still black? That is such a good question. All right, so yes, when you look at a picture of the sun looks yellow or maybe orange, and the sunspots look black or maybe brown. And a bunch of these things are not true. The first thing is, as you said, the sun isn't yellow, the sun is white. But there are different filters that astronomers use to be able to see the sun, and whatever kinds of features that they're trying to look at will reveal different parts of the sun. So if it's just a purely visible filter that they're looking through, then the sun will look a little more white. But if they're using, say, a hydrogen alpha filter, which lets them see some of the prominences and solar flares and things like that, then they're going to switch and the sun will look a little more orange. But it can really look like any color. It's sort of like you're seeing it in one color, one wavelength, the wavelength that corresponds to the hydrogen alpha filter, and then usually like a color is applied to give it something to make it so it doesn't just look gray. But as you say, it's weird though that the sunspots look black, and they're not. They're incredibly hot. So the temperature of the surface of the sun is 5,700 Kelvin. And the temperature of sunspots is in between 3,000 and 4,500 Kelvin. So they are definitely cooler than the surface of the sun. And they correspond to the colors, like at 3,000 Kelvin, you're looking at red, and at 4,500 Kelvin, you're looking at orange. So if you could take a sunspot and just move it away from the sun, there would be this bright orange glow in the sky. In fact, if you could just take a sunspot, like right out of the sun, and just leave it there, it would be brighter than the full moon, and it would look orange. But the sunspots are lost in the glare of the sun itself. Now, there's a couple of ways that you can actually see sunspots. Now, you never, I can repeat this like for an hour, never look through a telescope or binoculars at the sun. I mean, it's already dangerous enough to look at the sun, but if you do it with a magnification, then you can cook your eyes just like meat. And you do not want to do that. So you want to project the image of the sun onto something. There's a couple of ways. So one is you can set up a pair of binoculars, just hold them at arm's length and then aim them, and eventually you'll get an image of the sun coming through the binoculars and being projected down onto the ground. You can actually see the shape of the sun. You can see the sunspots across the surface of the sun. Or you can do that with, say, a small spotting telescope. You don't want to do it for very long because the sun will heat up the inside of your binoculars and will actually be able to kind of melt the internal components. I've ruined a telescope this way. So, and just once again, you do not look through. You hold it at arm's length and let the sun go through the binoculars onto the ground or a piece of paper, and that will let you see the sunspots. And then the other way is to get a pair of solar glasses. So there's lots you can buy. They're relatively inexpensive. It's like a sheet of metallic film that goes in front, and you're able to look through it, and it blocks most of the light coming from the sun, and you can actually see the sun. But you need really good eyesight to be able to see the sunspots. That's why I like using some kind of magnification. Again, don't look through your binoculars. Project the image. All right, you've probably noticed the Star Wars planet name that appeared over my shoulder during that first question, and this is a way for you to vote on the questions that you like the best. So just go ahead at the end of the video, after you've watched all the videos, you've seen all the planet names, and we'll we'll provide references in the show notes so you can pick one as well. Then write down the name of the planet for the question that you thought was the best. And then next week, we'll celebrate the winner. And so last week's winner was David McSween, who asked about hypervelocity stars. So everyone liked that question. Congratulations, David. Congratulations, me. We make a good team. All right, so don't forget to vote. Doug Neargarth, 236. The Earth has been broadcasting radio waves now for a good 100 years. How many star systems that we know of have our broadcasts reached? Humanity has been broadcasting radio waves out into the cosmos for about 100 years. And those radio waves have been moving away from planet Earth at the speed of light. And so there is this expanding sphere of stars that are enveloped within this bubble of radio waves that humanity has sent out into the cosmos. How many stars are within 100 light years of the Earth? The answer is we don't know. The problem is that we don't know how many red dwarfs and brown dwarf stars are within that volume of space. They're very dim. You pretty much can't see red dwarfs very easily without an extremely powerful telescope. And so astronomers are still trying to figure out how many red dwarfs are out there. But based on their estimates that they've developed so far, based on the ones that are closer, they're estimating that there's probably about 10 to 20,000 stars within that 100 light years of Earth. Now, only less than 100 are like big stars, the kinds of things that you can see with the unaided eye in the sky, and the vast majority of them are those tiny, dim red dwarfs, brown dwarfs, etc. So can those alien civilizations that live on some of those stars detect our radio signals? And the answer is maybe. The problem is that radio waves, the electromagnetic spectrum, as you broadcast in a sort of general way, then the strength of the signal falls under the inverse square law. So for every twice the distance that it goes, the strength of the signal drops by a factor of 4. And you can imagine as you go out and out into 100 light years away from us, the strength of that signal is incredibly low. We wouldn't be able to detect the strength of that signal today, but we do have a new instrument that's in development that would theoretically allow us to detect humanity from another star. And that's called the Square Kilometer Array. And this is going to be 1 square kilometer surface area of radio telescope. And in theory, it should be powerful enough when it comes online in the early 2030s. It should be powerful enough to detect the radio traffic control for like airports at a distance of about 100 light years. In other words, if there was some aliens landing airplanes 100 light years from us, we would be able to detect them, and vice versa. So right now, we wouldn't be able to detect ourselves, and we would assume that alien civilizations at our level of technology wouldn't be able to detect us. But in 10 years, we would just barely be able to detect ourselves. When we think about sending transmissions to an alien civilization or listening to signals from an alien civilization, the assumption is that they're going to be using some kind of beam. They're going to be directing the energy directly at the target, and then the strength of that signal doesn't fall off in the general sense if you're just broadcasting in all directions. Big E and H. How does gravitational assist work? I mean, the energy has to come from somewhere, or does it just appear to move faster because the probe isn't fighting the sun's gravity as much? When you think about the idea of a gravitational assist, when you think about a spacecraft approaching, say, Jupiter, you imagine the spacecraft is falling towards Jupiter, and it's falling faster and faster and faster, and then it goes past Jupiter, and then it's climbing the gravitational well on the other side. And I'm sure in your mind, you're imagining those two things balance out. It picks up speed as it falls down the gravitational well, and then it loses speed as it comes up the other side of the gravitational well. And that should just equal out and balance to 0, right? So how does a spacecraft get a gravitational slingshot? And a fairly significant one. I mean, they can move several kilometers per second faster when they do a gravitational slingshot. And the answer is they steal momentum from the planet. So yeah, if Jupiter was sitting there all alone and it was the only object in the entire universe and your spacecraft was approaching Jupiter, it would net out to zero as it went past the planet and came out the other side. But Jupiter is in orbit around the sun. It has an orbital velocity. And as the spacecraft is approaching Jupiter, the gravity of Jupiter grabs onto it and pulls it down into its gravity well, but it also pulls it up to its orbital velocity going around the sun. And so it's able to go from a lower orbital velocity to a higher orbital velocity, but it's actually going slower. Anyway, you gain energy as you approach the planet. And that's independent from you falling into its gravity well and you falling out of its gravity well. And so now you've got this additional speed boost that you get from being pulled up to Jupiter's orbit. And then you're able to carry that on as you fly off to wherever your next target is. And the energy doesn't come from nowhere. You are stealing a little bit of Jupiter's momentum as it's going around the sun. You are lowering Jupiter's orbit a tiny little bit because of your spacecraft. And the cool thing about gravitational slingshots is they work the other way as well. You can slow down by giving a planet some orbital momentum. And so this is used all the time to get closer and closer to the sun. Spacecraft will do a flyby of Venus or even Earth, and they will speed up the planet a tiny little bit, and that will slow down the spacecraft so that it's able to get closer and closer to the sun or whatever target it's looking to go to. So gravitational slingshots, gravitational assists are a really cool technique to be able to move around the solar system a lot faster and in different orbits than you would normally just through your propulsion system alone. Mr. Darcy. An analogy I use when thinking about an expanding universe is to visualize a balloon that is slowly inflating with matter on the balloon's membrane. However, the universe is flat. Can you help? Sure. And I make this analogy a lot here on the channel, but I feel like it's one of the fundamentals that if we can hammer this into everybody's brains, then they'll be able to examine various news articles and other videos and stuff out there. So that idea of a balloon with galaxies sitting on the surface of the balloon, and as the balloon expands, the galaxies are all moving farther away from each other. That works, but as you said, it's kind of confusing. And so the one that I like to use, and we've got a really cool graphic that we're able to apply when we talk about this, is instead imagine the universe as a grid, as a three-dimensional grid that just goes on forever in all directions. And you put galaxies at the various nodes on that grid. And then as time goes on, as the universe becomes less dense, the size of the grid gets bigger. The universe gets less dense over time, and these galaxies are carried away from each other. And so if you went to any point on this grid and looked in all directions, it would appear as if all of the galaxies are moving away from you. And if you jump over to one of those other galaxies and you look from that perspective, all the galaxies are moving away from you again. So don't think about the balloon, even though like I understand why they do it, because it does make sense to show that there's no special place. But the problem is then people sort of see that and they go, oh, but that's two-dimensional and we're in three-dimension. I can just see the balloon and there's a center in the balloon. Like, that analogy just falls apart. So instead, a grid in 3 dimensions that goes on forever, that is becoming less dense over time. Steve R. How will the future sample return mission to Mars find all the tubes dropped on the surface when blowing dust and Mars dirt seems to pile up quickly on the rovers that are there now? So we got some cool pictures from NASA's Perseverance rover last week showing all of the sample capsules that it's put on the surface of Mars so far. Now there's 18 capsules that it's collected so far that it's holding internally, and then it's dropped another 10 capsules onto the surface, and those are backups. So if everything goes as planned, Mars Perseverance will meet up with the Mars sample return mission, pass over all of the sample capsules in this really nice set. They'll be put into a rocket, it'll be fired into space and sent home to Earth. But if there's some problem with Perseverance, if it runs out of power, it's not able to complete its mission, then there will be a series of these backup sample capsules sitting on the surface of Mars. Now, the Mars sample return mission will be equipped with 1, maybe 2 helicopters, which are beefed up and will have the ability to grab these samples off the surface of Mars and bring them back to the return capsule. Like, I almost want them to fail so that they have to deploy the helicopters to scour the surface of Mars to bring those samples back and launch them back to Earth. But like, I don't want them to fail. Like, I want the whole thing to go and for them to not need them. Maybe a future Mars mission, human explorers come and find those samples and bring them back and study them on the surface of Mars. That's what I want. But you're asking, how will they be able to find the capsules if they're going to be sitting out there on the surface of Mars? And you're right. There is blowing sand on Mars. There is the dirt and grit on Mars that covers everything. But that gives you the answer. Like, if you take a look at Mars Insight, you can see this thick layer of dust that's covered the entire spacecraft, the solar panels, its robotic arm, everything. But it's like a thin film. It's not like a meter of sand is covering the rover. It's this tiny little film that you could wipe off with your hand if you could get there. And so we know that over the course of, say, 5 or 6 years, the amount of this sand that's going to build up over top of the sample capsules is going to be fairly limited. And of course, they're going to be setting the position so that they know where to fly to try to be able to find them again. So yeah, in 100 years, they would probably be gone. But in about 5 years, 6 years, they'll still be there and they'll be easy to find. The film on top of them won't be that bad yet, even if there's like a global dust storm. But remember, these are a backup, not the main way that they're going to be able to get the samples back to the sample return mission. Farmer John. So Fraser, crazy Canadian here, does the Earth have enough internal energy which humans could direct to steer Earth itself clear of the sun's red giant phase? No. There isn't enough energy available to humanity on Earth for us to be able to move the planet when the sun goes into that red giant phase a few billion years from now. But I'm trying to think, like, did you see the Wandering Earth movie? It's kind of like that, with these giant rockets that they put on the Earth to try and move it to, what, another star system or something? No, you wouldn't do that. But there is a way. And it actually relates to the question earlier on about gravitational assists. So if you take an asteroid and you fly the asteroid really close to the Earth and you do a gravitational assist, then you can steal some of the orbital momentum from the asteroid and you can give it to the Earth. And what that will do is that will cause the Earth to rise a little bit in its orbit. It'll slow down, but it will be higher from the sun. So as the sun is increasing in its heat and intensity, you can slowly move the Earth by bringing asteroids close to the planet and doing these gravitational slingshots. We're going to need to start a little sooner than you might think because the sun is actually heating up all the time. And over the next, say, 500 million to a billion years, not global warming, but 500 million to a billion years, the temperature on the planet will get so hot that the oceans will boil and the surface of Earth will be uninhabitable. But if we bring these asteroids by Earth about once every 10,000 years or so it doesn't have to be a lot, then you can slowly shift the distance of the Earth from the sun bit by bit by bit to match the increased output that's coming from the sun so the Earth stays comfortable all the time. And there's an even cooler trick, which is that you can take your asteroid and you can do a slingshot past Earth. And if you time things right, you can then do a slingshot past Jupiter. And so then you can steal more momentum from Jupiter, have your asteroid come back to Earth, give that momentum to Earth, go back to Jupiter, and just go back and forth and back and forth. And you will slowly steal a little bit of Jupiter's momentum, maybe bring it a little closer to the sun, and you'll give all of that momentum to the Earth and keep it slowly drifting away from the sun to match the amount of heating that's happening from the sun to keep us all safe forever. And then you can run this process in reverse once the sun is done with its end-of-life temper tantrum, bring the Earth back close to the white dwarf star and nestle it in really close, and then you would have comfortable temperatures for billions more years. So, I mean, that's geoengineering at a massive scale. It's a mega project, the likes of which, but like to just get an asteroid moving on the perfect trajectory and make tweaks to it every 10,000 years or so, that doesn't sound so hard. If you like my answers to your questions, as well as the other things we do at Universe Today, consider joining our Patreon club. This allows us to keep a minimum ads for everybody. Like, as you can see, there are no ads in the middle of this video. As a patron, you also get an ad-free experience on universetoday.com for life. Even if you unsubscribe, you'll get ad-free videos, early access to interviews, as well as other perks that are exclusive to our Patreon community. Thanks to everyone who has already subscribed, and welcome to the recent newcomers, Reed Bowman, Colin, John Kosanke, Richard Chase, R.K. Young, Tim D. Zwicky, Frida Marie Leisted, B. Michael Neal, Wendy Spacenut, and Koibu. Join the club at patreon.com/universetoday. Brian Walker. If a large star within a dense star cluster went supernova, would it affect a nearby star, or the distance between stars still too great? If you had a dense cluster, maybe the stars are about 1 light year apart on average. In, say, a globular cluster, or if you've got like some kind of new forming star cluster, then the stars are going to be about a light year apart. And if one of those stars went supernova, it would have no appreciable impact on the stars around it. It might increase the amount of radiation in their area for a little while, might collapse nearby clouds of gas and dust, but it wouldn't do any damage to the star. Now, planets in that area that are orbiting those stars, if you're within about 50 light years, it is trouble. The impact of a supernova blast can scrape away your planet's ozone layer, and then there's radiation that's coming from space thanks to the supernova, and so it's thought that some mass extinctions in the past have happened from a supernova being too close to us. Don't worry, there are no stars that are big enough to go supernova, close enough to cause us any damage in the near future. Where it can impact a star is when you've got 2 stars in orbit around each other. One of them is one of these supermassive stars that dies as a supernova and blows itself apart completely. And the other star that was orbiting around it is now completely untethered and can fly off into space, leaving the cluster forever. And it could be going fast enough to actually be on an escape trajectory to leave the galaxy entirely. Commander Wolf. I'm doing a school project essay about space, and I would like your opinion on the question. Should the US continue using their resources on exploring space, and why? All right, so I can't do your homework for you, but I'll give you my opinion, and then you can reference me, and then show how your footnotes work. So should the US, and really the rest of the world, I mean, I'm not American, so I'm not going to tell Americans how to live their lives. I'm Canadian. But should we explore space? Should we spend money on doing that? And obviously my feeling is yes, absolutely. So why? Like, what is the value of exploring space? And, you know, people give a lot of answers to why we should explore space, because there's resources out in space, there's power out in space, because we will develop better technology and we will use that down here on Earth for various strategic purposes and defense and stuff. And that's all fine. But the reason that we should explore space is because we're curious, because we want to know what's out there. And the only way to find out for real, and not just in our imagination, is to go there and look. How can you find out if you don't go and look? And curiosity is enough. Curiosity has gotten humanity to the place that it is today. When you look at all of the technology that we have around us, all of the computers and the internet and the communication systems and lasers and satellites and all of this stuff and textiles and I could just go on forever. Most of that, all of that came from curiosity, came from someone saying, I wonder what happens if I do this. I wonder what's over there. I wonder how this works. How deep can we dig? What's this made out of? Again and again, we ask that question. And when you think about the universe, Earth is a teeny tiny little bit of everything. And so the amount of curiosity that we should have for the rest of the universe is dramatically higher than the curiosity that we have for here on planet Earth. So why do we go? Why should we spend money? Because we don't know what's out there. We don't know yet. And it's always worth exploring to learn more. And the benefits come later on in ways that are completely unexpected, but they always seem to come. Bill Gates. Hello, Fraser. I'm 11 and I listen to your podcast at night, and I was wondering if you could tell me if it is possible if we somehow harness the power of a wormhole, could we time travel? Very cool that you're listening to this podcast while you're 11. It sounds like me. I would have totally dug my YouTube channel if there were YouTube channels when I was 11, but we didn't. I just had books and I had to read them. It was very boring. But I did buy my first telescope when I was 14, so think about that. Can we use wormholes to time travel? Well, theoretically, yes, right? A wormhole, I'm not going to go into all the details because it's like, I don't know, complicated physics stuff, but in theory, you take a wormhole and you establish this portal between two places in space, and then you walk through it and you appear on the other side and you're at the same time. But if you then take that wormhole and you put it on a spaceship and you fly it at close to the speed of light, well, now this wormhole is moving relativistically at a different time than the one that is stationary here on Earth. You fly it away, you then leave it on some other planet, and now when you step through the wormhole on one side, you're coming out the other side, and you're coming out at a different time than when you enter in. And so theoretically, you could go backwards in time, you could go forwards in time, depending on which end of the wormhole you go through. Now, this is to be said with a giant caveat, which is wormholes aren't real. Now, maybe they are theoretically possible, and every now and then we see some physics paper that comes out that suggests a way that wormholes could be developed, or maybe wormholes could be seen and detected out there in the universe, but we have no physical evidence that these things are real. So once someone is able to develop a stable wormhole, then someone is definitely going to try putting that wormhole in a spaceship, moving it close to the speed of light, and then using that as a method for time travel. And like when I think about all of the methods of moving through space, all the science fiction ways, we think about Star Trek, warp drives, hyperdrives, my favorite's Stargate, that you could just put on your hiking shoes, step through the portal, and be on a planet that is tens, hundreds, thousands of light years away, and you didn't even have to get in a spaceship to do it. So I will take wormhole travel over every other science fiction method of travel, no question. Polyps conglomeration. What may have killed the Chinese rover? From what we can tell, the Chinese Zhurong rover on the surface of Mars is dead. In fact, we've got some new pictures from the Mars Reconnaissance Orbiter that shows the rover from orbit and shows that it hasn't moved in a few months. It was moving and now it's not moving anymore. Now, we haven't got an official announcement from China to say, yes, we admit the rover's dead, that's that. Instead, we've just heard rumors and we've got these pictures that it's no longer functioning. We haven't heard any new science coming out from Zhurong. So at this point, I think it's safe to say it's dead. Why is it dead? We don't know. But we can assume that the thing that takes out solar-powered Mars rovers is dust. And so it's taken out Opportunity, it's taken out Insight, it's taken out other rovers. We can just assume that that's what took out Zhurong as well. Like, until anyone tells me otherwise, I'm just going to assume in my mind that its solar panels were covered with dust. It wasn't able to wake itself up after a long Martian night. It wasn't able to keep its batteries warm enough. The batteries froze, they died. It wasn't able to restart when the sun came back out, and it's gone. But hopefully, people from the Chinese Space Agency will tell us what's going on, and we'll be able to give an official explanation of what happened to the Chinese rover. And it's a really cool rover because it has a ground-penetrating radar system built in. There's one on Perseverance, but the one on Zhurong is really powerful and can go really deep, like can peer into the regolith down to a depth of about 80 meters. And that's deep enough to be able to see if there's like deposits of water underneath the surface of Mars. It didn't find any. They tried, but also to be able to see the size and the shape of the regolith going underneath the rover's feet. And so, like, I'm a huge fan of these ground penetrating radar systems that the Chinese have installed on their different rovers. They put a system on their moon rovers, and they put this one on the Mars rover. And this is like one big piece of the puzzle, to be able to look under the surface of Mars deep enough to be able to see if there's any deposits of water near the surface. So pour one out for Jurong, and hopefully I'll be able to give you some kind of an official explanation in the future. Twisted Whiskers. Fraser, I can't see anything beyond the moon with the naked eye at my home, so why should a telescope in a nearby city at a university see anything more? I'm assuming if you can't see much more than the moon, you live in a very bright city, so the light pollution is so bad that you can really only see the moon. But that's not true. You could see some other stuff. And in fact, right now is a really good time to test what you're capable of seeing, because Venus and Jupiter are very close in the night sky to each other, and depending on which day you watch this, they're close to the moon. But I think they get to their closest point on March 1st. And so go out after sunset, look to the west, and see if you can see Jupiter and Venus in the night sky. I'll bet you can. And so they're very bright. And I'll bet you can see some other planets as well. You can probably see Saturn. You can probably see Mars. You just need to know where to look. Probably the light pollution has been so bad in your city that you just don't bother, but they're there. And when it comes to the moon and the bright planets, being in a city with a lot of light pollution doesn't really matter when you look at the planets through a telescope. So if you go to the nearby university and you look through their telescope, you will see an amazing view of Jupiter and Saturn and Mars and the moon and Venus and even Mercury. They all look great. Pretty much exactly the same, or not quite exactly the same, but still really good compared to a place that doesn't have any light pollution. It's the fainter objects that you're not able to see very well when you have a lot of light pollution. Galaxies, nebulae, clusters, things like that. But still, I mean, there was a big observatory in my hometown in Vancouver, and you could go and you could look through the telescope and you could see the Great Globular Cluster in Hercules, you could see the Ring Nebula, you could see Andromeda, you could see a lot of stuff just because the telescope is very powerful and it's able to brighten objects that would be lost in the glare to a smaller telescope. It can still see it. But to really observe from the light of a city, you need to have some kind of filter on your telescope. You can have like a hydrogen alpha filter that just lets in one very specific wavelength of light that is not blocked by light pollution. And so there's hydrogen alpha, there's one that lets you see sulfur, there's one that lets you see oxygen. And so often astrophotographers will have these very special filters on their cameras that let in these wavelengths of light that are not hampered by light pollution. And so you can be in the middle of New York City, you could be taking pictures of nebulae and galaxies and all that, and the pictures look amazing, even though you have horrible light pollution and you wouldn't be able to see it in any other way. So how can a telescope do it? They're very powerful, and in many cases, they have filters on them so that you can sort of see the wavelengths that are not disrupted by light pollution. Like, even if you live in really light polluted skies, I think it's still worth it to buy. Like, if you're into space and you want to see Jupiter and Saturn, and you want to see the moons of Jupiter, and you want to see the craters on the moon, you want to see Mars, see its polar caps, buy a telescope. You know, a nice Dobsonian telescope will give you a really good view to those objects, and then you can go put the telescope in the car, go to a place with darker skies, and see a lot more. Surak of Vulcan. How exactly can astronomers tell if an asteroid or meteorite is interstellar in origin? All right, so those are two different things. How can we tell if an asteroid is interstellar in origin? And the way astronomers do that is they look at the orbit of the asteroid. Normally, things that are in the solar system, they are orbiting around the sun. They are in some form of ellipse, which means that they're just going to go around and around the sun forever. Like either almost circular or just some kind of elongated ellipse, like a comet's orbit. But two objects have found on a hyperbolic orbit, which means that they're not going to return to the sun. And so for them to have this hyperbolic orbit, they must have come from outside the solar system, and they're going to return to outside the solar system. So by measuring the orbit, calculating that it is a hyperbolic orbit and not a nice ellipse like what you would expect, that tells you that the object is interstellar in origin, or if it's not interstellar in origin, it will be interstellar soon because it's leaving the solar system and it's not coming back. What about a meteorite? To find out if a meteorite is interstellar, then you examine the characteristics. Essentially, you age date the material inside the meteorite. And one of the ways that we learned the age of the solar system was by measuring the age of meteorites. And they found that all of the meteorites that they got their hands on, they all seem to be the same age, about 4.5 billion years old. But since then, astronomers have found grains inside meteorites that are older. In other words, that they came from something else that was older than the solar system, were sort of meshed into meteorites when they landed on Earth. And so there's just little grains inside meteorites that came from an earlier time than the solar system. I don't think anybody's found like an interstellar meteorite where the whole meteorite is older than the solar system, but they're there, they're out there, they have to be. Right? If we've detected interstellar objects passing through the solar system, they have to be there. And I know that there was one object that hit the Earth's atmosphere a couple of years ago that appeared to be on an interstellar trajectory when it hit the Earth and is sitting at the bottom of the ocean somewhere. And some astronomers have proposed that we go looking for it because it's a very special meteorite. And if they could find it, then they would be able to gain information about some other star system just by studying the chemistry of the meteorite itself. All right, those are all the questions that we had today. Thank you everyone who asked them in the YouTube comments, as well as the people who stuck around for the live show and asked them. Remember, we do this show every Monday at 5 p.m. Pacific time. Now, vote for the question that you liked the best. We'll count them up and we will celebrate next week. If you want to stay on top of all the important space news, join my weekly email newsletter. I send it out every Friday to more than 60,000 people. I write every word, there are no ads, and it's absolutely free. Subscribe at universetoday.com/newsletter. You can also subscribe to the Universe Today podcast. There you can find an audio version of all of our news, interviews, and Q&As, as well as exclusive content. Subscribe at universetoday.com/podcast or search for Universe Today on Apple Podcasts, Spotify, or wherever you get your podcasts. A huge thanks to everyone who supports us on Patreon and helps us stay independent. Thanks to all the interplanetary researchers, the interstellar adventurers, and the galaxy wanderers. And a special thanks to George, Jeremy Matter, Jordan Young, Tim Whalen, Dave Verabioff, Josh Schultz, and Andrew Gross who support us at the Master of the Universe level. All your support means the universe to us.